Okay, thank you.
Si vous voulez, vous pouvez l'utiliser. Le micro, c'est surtout s'il y a des gens qui écoutent sur YouTube. Ça marche peut-être.
Ah,
Peut-être. Ça marche pas tout le temps.
So we're going to the second question on interviewing and social media analysis. We have people, and we start with the one given by Untitled Chapter.
So hello everyone. First of all, thank you for attending this presentation. My name is Sancho Perez, and I'm going to present the work done along with Manuel Couto and Javier Parapar, which is titled Temporal Work Embedding for Early Detection of Signs of Depression. Okay, I'm going to begin this presentation giving a bit of context and talking a bit about the motivation where this work is located. So I think most of you are already aware of the harmful effects that depression can bring to the general society. Depression is one of the most debilitating mental health diseases. In worst cases, it can even lead to suicide, but also moderate cases can lead to other harmful effects like alcohol addiction or drug abuse. And it is also well known that proper interventions in the early stages of depression are crucial to minimize further consequences and the impact of the disease. And in this context, a big part of mental health research has always been focused on the link between language and mental health. And the proliferation of social media has opened a way for many researchers to demonstrate that this is a promising channel, is a promising tool to detect pieces of evidence from different mental disorders. So basically, in this work, we propose a framework that allows us to evaluate if work evolution over time can reveal the presence of different depressive tendencies. Okay, to explore our intuition, we addressed the task of early detection of depression, also known as EDD. And here I have to highlight a small point about what is special of this task. Because conventional settings of depression detection always assume that methods can access to the whole writing history of the users, of individuals, before making their predictions and their inference of the health status of the user. However, EDD goes beyond this setup and believes that systems that can emit the alerts as soon as possible have more potential in the clinical use for practical applications. So basically, in EDD scenarios, users' writing history are chronologically sorted into different temporal chunks, and each chunk contains a percentage of the writings. So the methods, the systems need to sequentially process each of the chunks sequentially. And once the systems are confident enough, they need to decide if they can emit an alert of the user or consider that, okay, this user is okay, there is no risk. However, if they are not confident enough, if they couldn't bring evidence of the user, they can always choose to request a new chunk, and they can access to more information of that same user. Okay, most of the prior work that addressed this task focused their effort on different depression-specific features, and such as the exploit of different depression lexicons or psycholinguistic features, and in our proposal, we only focus on the language evolution of individuals. Our main proposal is based on one idea that is individuals developing depressive symptoms will eventually change their language usage. These individuals will experience new emotions, new thoughts, new feelings, that as a consequence, many words will appear in previously unseen contexts. So what do we do? Our approach tries to locate these word shifts from one time step to another and quantifies these meaning changes. To do this, we adapt temporal word representations to calculate the magnitude of word movements over time. So our approach relies on two main components in the construction of two types of work embeddings or work vector spaces. The first one is the reference vector space, and the second one is the dynamic. And now I'm going to briefly explain these two main components. The reference space is an atemporal vector space that remains constant in all the process of our method and tries to capture the neutral and the context of the words in a neutral context. Yeah. And on the other hand, we also calculate different dynamic vector space that correspond to one different chunk. So, for example, here we have a user, and we have different chunks for the same user, and we calculate a different dynamic temporal chunk space for each chunk. And then we can always compare and calculate the distance between each temporal space and the reference space. And these distances are the only feature and the only features considered as inputs to our classifier. Okay, to address this proposal, we experimented with two different types of temporal work models. The first one is an adaptation of temporal work embeddings with a compass, which is compass TRAC, and it's based on the word-to-vector architecture. We are working here with the static embeddings. And for the creation of the reference vector space, we simply use the CIGO standard architecture to train the whole training set, considering all the users of the collection. Dynamic vector space will leverage this reference space for alignment. What do I mean for alignment? When you compare two different vector spaces, you need to make sure that they share the same coordinated systems. That's alignment. And then we train different vector dynamic space for each chunk. And then we can always calculate the distance of the words. In our second experiment, we tried with contextualized embeddings based on the famous transformers architecture with BERT. And we adapted a word called dynamic contextualized word embeddings, which stands for DCW. And in this case, for the reference vector space, we simply use the BERT embeddings that are already trained in large collection of documents. For the dynamic embeddings, here the words are first mapped to dynamic representations using the output of the feed-forward network, and then are contextualized using the standard training procedure of BERT, which relies on masked language modeling. Okay, to evaluate these two experiments, we use the dataset delivered by the ERWIS collection, which is actually the standard benchmark for early risk detection. We use the collection of 2017 and 2018. Regarding to the metrics, we use standard evaluation metrics like F1 and also time-aware metrics that were proposed by the risk organizers. These two metrics are error metrics, so the lower the better, and start penalizing the systems when they last before making the inference. And for the baselines, we simply consider the best results, the best previous works for each of the metrics. So if we focus first on the first collection on 2017, we can see that only considering the language evolution of individuals, we can still achieve competitive results in terms of, especially in terms of time-aware metrics. So, for example, in R5, we are currently state-of-the-art with the DCWE method. And what this means, R5 is an error metric that starts penalizing the methods after they process 5 publications. And it is the same for R50s, but they start penalizing the methods after they process 50 publications. And we can also see here that for F1 results, we have a drop in the performance, and this is quite rational because for our methods, we maximize for the time-aware metrics. And then for the 2018 collection, our results follow a similar tendency. And I note here that if you look at the absolute results of the time-aware metrics in comparison with 2017, we can see that the results improve, which we believe that with more training data, our methods can get better and better. To discuss our work, we can say that our framework is competitive with state-of-the-art solutions, especially in time-aware metrics. That also our framework do not rely on the precision-specific features or elaborated decision mechanisms before meeting the alerts. And this makes our method quite flexible, so it can be adapted to investigate, to aggregate all features to other representation-specific ones. To conclude our work, we explore the potential of language evolution in early detection from social media and demonstrate the usefulness of considering words in such features, obtaining competitive results. And yeah, the ability of our framework allows us to extend this idea not only to other depression-specific features, but also to similar diseases without additional efforts. And that's all. I hope you enjoyed this presentation.
The idea of dynamic embedding representation of words is very interesting, and I think that actually it could have many applications like online reputation management, to analyze the context of the name of a company or the topic over time. Did you think about the application of this approach to other problems, and did you link this idea of dynamic word embedding with approaches from other research lines?
Yeah, that's an interesting point. Not yet. We are now proposing to extend this same idea to other similar diseases to see if the pattern of language evolution can be extended to these diseases. But this type of work can be easily extended to other many domains. So yeah, that's definitely an interesting point. Yeah. Thanks.
Sorry, yeah, I have first a clarification question on the slide. So, I'm not sure what feature you have. Is it distance per word you consider? Or
we simply use the cosine distance between the same word from the temporal chunk and from that same word with the reference space. So we have, let's say, for the word life, let's say, it is supposed that in the reference space it will be related with some other neutral words like okay or interesting or exciting. And in this case, if the user starts developing depression here, it can be associated with other more alarming words like depressing or enjoyable or similar words like that.
Okay. And my second question then would be, I mean, if the person was depressed first and then become less depressed, could you detect this with the same system, or is it because there is a symmetry in the documentation, which might be a bit concerning?
Yeah, that's an interesting point as well. For the moment, we didn't because we don't have that information in this collection, but we are going to be working with new novel collections that explicitly say when the user starts to develop depression symptoms. So based on that, we can focus on the specific temporal chunk where the user started to be good, to start being a bit depressed. And from there, we can extend and also add some new features to the work. Yeah.
Thank you. Users on social, I believe you use social media text, right?
Yeah, from Reddit.
Users on social media sometimes have a tendency to change their activity over time. Is your model in any way sensitive to these activity changes?
Not for the moment, but you can see this kind of work can have a lot of future direction lines. But yeah, because as we are working with Reddit datasets, this kind of datasets have a lot of noise because users tend to not only talk about depression of their lives. There are also a lot of out-of-context publications. We are trying to implement the same methodology, but before computing the features, first doing a pre-processing step to eliminate the noise that can possibly exist in the user's writing history. Yeah.
Cool. Thank you.
Thank you.
Hello everyone. My name is Fanny Varanamsu, and I'm from Untitled in the team 6, and I will present you today to our my work on multitask learning for speech and aggression detection. So this is a preliminary work on this task. So this is our first try on using multitask learning for this kind of detection. So for introduce a little bit, as we know that everybody use social media right now, and the way that people communicate, they changed, and we have seen that there is a lot of cyber aggression, personal aggression, because of anonymity. Everybody is right now courageous to do what they want in the social media. So normally they don't know, they do it online. So there is a need of monitoring of user-generated content to avoid this kind of abuse behavior online. And it was an interesting topic for a few years right now. And for us, we try to use multitask learning to resolve this problem. So our work will use multitask on two shared tasks, different but related one. The first shared task was about aggression and cyberbullying detection. It is called TRAC. And the objective was to classify a text into three categories. The first one is overtly aggressive, when the aggressivity is expressed directly. The second one, covertly aggressive, the aggressivity is expressed in indirectly way. And the last one is a non-aggressive text. For the second task, we choose HASOC. It is a hate speech and offensive content identification. During this task, the objective is to classify text into two categories. The first one is positive, which contains hateful and offensive content, and the second one not hateful and offensive. So there is already a lot of work in abusive language detection. The majority is supervised learning, and there is a lot of work based on pictures and using classical machine learning to deep learning. And also we use a few times right now that a lot of researchers use transformers like BERT. And right now, the multitask learning is also very used. But as we have seen right now, they don't for the multitask, they don't use two shared tasks in the same way. They use like a downstream task. For example, for the first task is detecting hate speech, and the second task is emotion detection. So there's a relative task like this. So for us, we just use two shared tasks on abusive language detection. So for our approach is it is a first try. So we use a simple model one. So for each task, we develop one transformer encoder, and for simplicity, we just use this and share the weight of encoder. So this allows us to implement simply, and also for pre-processing, it is simple because as we have different model for each task, so we just have each model has the same its own processing. So the data set we use is from the two shared tasks. So for HASOC, we use the 2019 and the 2020 data set. So we see some statistics about data set. And for TRAC, we use the data set from the edition 2018 and 2020. So all the text are in English. We don't use the other text because for TRAC they have for Hindi and German languages also, but for us we don't. We just choose English one. So as a result, we take as a baseline just the transformer model Roberta, and we compare the results. So we have the same result as the baseline, slightly better on HASOC 2019. And if we compare to the participant of each shared task, we saw that on HASOC 2019 we are achieved also a slightly better result. And for TRAC, the result is promising, but need a little bit of work again. So as a conclusion, as a first try, it is a promising result because we outperformed a little bit, achieve the simple fine-tune model, and also achieve the good result comparing to the participant in TRAC and HASOC. As a future work, we will try to improve our model architecture by using more complex one or other ones. Also, testing other transformer-based model, and of course, more analysis on data set, and including other related tasks. So thank you for the presentation.
Since you tackled the problem of hate speech detection, and I see that it's a binary classification task, and since it's a text classification, so how do you handle out of vocabulary words? Out of vocabulary, like the words which are not in the vocabulary, such as spelling mistakes, grammatical mistakes, because I have worked previously in hate speech detection, and most of the work they do, they mostly fail in this task. So do you have any idea regarding how you are going to progress, or if it's
Yeah, for now, we just assume that there is no spelling even. Of course, there are a lot in the data set, especially in TRAC. But yes, this is also in maybe in the future work to see that how to deal with the spelling one. And as we used just the transformer used, so even with the misspell, it will be interesting to see if processing the misspell before will increase the model or not. It's a good question. I have no answer for it now, but it's a good idea to see effectively if it will increase the result in this vocabulary.
Thank you.
What's the role of each of the two tasks? What do you know? What can you expect from each one of the tasks? You have 3 tasks.
I have two tasks, but the image is show 3 tasks, but I have 2 tasks.
Yeah.
And the aim to having 2 tasks is like to try to using the multitask learning because it is a parallel learning to improve the result. So to use the information from the other task into the other task. Just we want to see if it can bring something to improve the result for the other task.
So you already have results for a morning task?
Yes,
Okay.
as we said in the parallel, we just one task, and for all the participants also, they just focus on one task and don't use other data set.
Okay. Okay. Thank you. Other question? Yeah. Thank you. Next, the last speaker. Is okay?
Prasad is fine.
Okay.
Is it fine if I stand?
Good afternoon to all present here. I am Mr. Prasad. I'm a first year PhD student at TRAC. I work in the domain of NLP, deep learning, and information retrieval. And my work concerns text classifications in the term of legal domain. I won't speak out the whole topic, it's quite long. So moving forward with that, while automate judicial process, doing so might help propel the slow judicial process. Like some cases take a lot of time. The time and space, like it will provide the court the required time and space to focus on other aspects of the judicial system. And among other advantages, it can help decongest the court cases. And for some people like us, we don't know the real rules and law and regulations of how the court cases goes. So it can give you an estimate of how your case or someone else's, you might know that how it can lead to how the outcome can be, and it can help you decide should you proceed with a lawyer or should you proceed with the case, or it can help you make a good judgment, which will save a lot of money and time with respect to the common public. How do we do so? Is like this paper mostly concerns the first part, which is the method to accurately predict the best probable decision from case facts. Regarding the explainability of the decisions, we did not consider in this paper because it was underway while writing this paper. That's a future work. So any questions regarding that, I won't be able to put forward. But moving forward with the first topic, which this paper concerns, there has been a lot of related work in the past regarding this. Giving you an overview just in 2 points. Most of the related work were mostly in civil court cases or criminal cases. That means they were specific. Here, we are trying to focus on general legal cases from general legal text. It does not mean it needs to be from civil or criminal or some other specificity. And
in our work, there's a slight difference with like from the previous work. What we are trying to do is we're trying to do text classification from unannotated and unstructured large documents. These are quite long, like around 30,000, 40,000 tokens. While in the previous work, it's mostly concerns detailed annotated data sets, and they were not, I mean, even they are long, but still they are very detailed. So there have been a very few research in our focus, and our idea is somewhat similar to what has been done by Malik et al. We have taken their data set, thanks to them that for contributing their data sets for our work. As per terms of copyright, we cannot share this data set, but it can be accessible from the authors. So basically the task formulation is such. The legal documents are mostly language oriented text. So the basic idea is to do a simple text classification, and the problem or challenge with this task, it might seem so simple, but it's not so simple because the texts are quite large. They are unannotated. They have only one or two, like they have just a binary label, just either it's accepted or rejected, and they are very unstructured. So if you want to extract a lot of information, like if you know, you won't know that where the facts are, where the decisions might be, because it varies from cases to case. So these are the main problem. I thought of showing you how a legal case looks like, but maybe in the question answering session I'll show you. But right now I'm moving forward with the slide. This research mainly concerns these three topics. I mean these 3 points. First, we are trying to show that domain-specific pre-training is better than general pre-training, which is but excellent. Better as in terms of it can be adapted well to these domains. That means it can be adapted to a specific domain. Here, the legal text. In order to process long sequences, we have used hierarchical transformers. The methodology of how it works will be shown in the next slide. And we try to see if the attention mechanisms, like general attention mechanism, which is dot product or multi-head attention, their variance, how do they improve or how do they adapt to the hierarchical models. So going to the details, we have used one domain-specific pre-trained model, which is named as LegalBird. The reason why we use that because like to retrain, it takes a lot of time. It was already available, and our data set was in English. So this was the one which was available, which we took forward to just see and compare whether it is better than Bird or XML. The hierarchical transformer architecture is somewhat, which you can see in a short sentence. It is what you do is you chunk down a long document or a long sentence. You take the CLS embeddings. Those transformer model can be fine-tuned, or it cannot be. It depends on what transformer model you use. Accumulate all the CLS embeddings, pass those CLS embeddings through RNNs, and then you apply your dense layer or whatever layer that you want to do the classification. So the attention mechanism which we have worked upon, they work on the RNN level, they don't work on the transformer part. So we use some variants of multi-head scaled output attention. The variants are like we took some like query can be taken from the last output of the RNN, and key value can be from first output of the RNN, or it can be directly from the CLS embedding. So we just experimented with some of the combinations. To show the data set, this is the data set which we use to work. This is known as the Indian Legal Document Corpus, provided by the Supreme Court of India. It's like the highest court of India. The data set is divided into 2 parts. I won't bore you with much of the details of the data set, but ILC multi is the bigger one which we focus on because it generally relates to the general type of legal cases. Here, petition means if you go to a court, you file your case, there is a decision. If you're not satisfied with your decision, you can file the case again. That means petition. So for all petitions which are having a single decision across all this petition, that is ILDC single. For ILDC multi, the decisions of the cases changes, which is mostly the general scenario. So these are the results. I'm happy to see that we were successful in order to prove what we are trying to say, with the result that we had an approximately 4% increase with domain-specific models. As if you can see, is it visible? I'm not sure, but from ExcelNet, which has the highest in terms of general language model, we have an improvement of like 0.738, like which is approximately 4%. Hierarchical models improves the legal words performance by 8%. So in overall, it combines up to like 12% of improvement. Because it is able to handle longer sequences, though it's very novice, like it's in its mechanism, it's very simple, but still it is able to handle longer sequences. With the use of dot product attention and multi-head attention, we could not see much significant improvement, though the improvement was slightly better. Like if you see, it's like 0.8 for like legal bird fine-tuned, like it's just 0.81 with accuracy, but with other, it's like 0.00. But it's not much, but it's a slight improvement. In conclusion, we explored
Et en fait, il ne faut pas utiliser pour rentrer son, pour rien. Pour rien.